Hello all, I am Swadeep Asthana and I am a part of OpenShift networking team at Red Hat. Today I am going to talk about user-defined networks, which are recently introduced in Red Hat OpenShift. Today I will walk you through the concept of UDN and how does it work alongside its benefit, types and their differences. So what is UDN? In OpenShift, all pods can talk to each other by default. Network policies are used to provide isolation between the namespaces. Also, network attachment definitions are used to define the multiple network interfaces to the pod. As we all know that, we have to be extra careful while creating the network attachment definitions because they can bring the whole application down if wrong configurations are provided. So to manage all these, we have introduced UDN, the user-defined network. It is a customizable network configuration. It provides default isolation to tenants or namespaces. UDN can be namespace scope and cluster scope, specifically made for the cluster admins. Primary UDN for default network of a pod, and secondary UDN for additional network on a pod. It can operate at layer 2, layer 3, and local network, which is basically a provider network. So why we need UDN now? As I said earlier, UDN is very helpful for following use cases: namespace isolation, multi-tenancy, VM migration, overlapping IP addresses, integration with external networks, performance optimization. So what are the benefits of UDN? So the benefit of UDNs are it provides better isolation, it provides multi-homing, it supports flexible topology, it also supports all Kubernetes API. It is very useful for live migration of the VM where the persistent IP address is needed. And it also uses legacy integration. User-defined network custom resource definitions. So, what are user-defined network custom resource definitions? So we can define UDN using user-defined network or cluster user-defined network, CUDN. Once any of these custom resource definitions are created, then Multus CNI starts working to attach the multiple network IP addresses to the pod. Once these CUDN and UDN are attached to the pod, then we can verify the networks in the annotation section of the pod. There are two roles which are supported by UDN and CUDN, and those are primary UDN and secondary UDN. Primary UDN are attached as a default network for a pod, whereas secondary UDN works as the additional network for the pod, which does not allow the external traffic. So what are the limitations of UDN? So in limitations, you cannot update UDNs once it is created. As a part of the DNS limitation, the Kubernetes DNS does not aware of UDN network. Host network pods are still not supported with UDN. Only primary UDN support network policies. That too, you cannot define them for all namespaces. So the types of UDN and their functions. There are basically three types of UDNs, namely layer 3 UDN, layer 2 UDN, and Localnet UDN. Layer 3 UDN in primary role supports full routing for the pod to the external traffic and for pod to pod traffic. And layer 3 UDN with secondary role, it only supports pod to pod as there is no source netting happening at the node level. Layer 2 UDN with primary role works in flat layer 2 domain, which is ideal for VM live migration. Layer 2 with secondary role, isolation is provided at the layer 2 segment of the network traffic. Localnet UDN is only supported for secondary role and it allows pod to communicate with provider network directly without S-netting at the node level, which is one of its exception as well. So when I talk about the exceptions, so exceptions of UDN includes the Kubernetes health checks. As we all know, the pods has default network provided by OVN, which works on the interface ETS0. But in the case of UDN, the ETS0 will only be used for Kubernetes health checks. And the second one is the Localnet UDN. So Localnet UDN bypasses the S-netting at the node level and communicate directly with the provider network using their own IP addresses. So how primary and secondary UDN work in OpenShift? So this is how UDN looks when created under a namespace. Once this UDN is created, it creates a NAD, network attachment definition, which you can see at the right side of your screen. And this is how the cluster user defined network looks like. This cluster user defined network is created under namespace 4 and namespace 5, and it creates the network attachment definition in namespace 4 and namespace 5. So this is the network attachment definition created by cluster UDN. Now demo. So here we are seeing the 4.18 cluster where I'm trying to reproducing these scenarios. So here you can see I have created the namespace for case 1, where the case 1 is saying we need to test UDN isolation among pods deploying different namespaces, and each of them has UDN configured. So for case 1, I've created two namespaces named blue and green. These namespaces has the label which is required by the UDN. Now I'm going to create UDN in both of these namespaces. So as you can see, both these UDN have different networks. So now the UDNs are created. As you can see in the status section of the UDNs, the network attachment definition has been created. If we verify the network attachment definition, we could see that two network attachment definitions are there in green and blue. Now I'm deploying the pods in both of these namespaces. Pods should be running with UDN network. So as we can see, the pods are in the running status. Now I'm exposing deployment to create a service for these pods. As you can see, we have created two node port type services for blue and green deployment. Now we are going to check the IP configurations inside blue and green pods. As you can see, we have the UDN interface configured and it's matching the subnet which we have provided in the UDN configuration. Now I'm checking from blue pod, are we able to access the blue service? As we can see that it is a success that we can access the blue service from a blue pod. So that is expected. Now I'm checking whether we can access blue service from a green pod. And this is a success for the scenario. Now case 2. Case 2, we are going to test the interpod communication where we are using cluster UDN. So for cluster UDN, I have created three namespaces, the Marvel, DC, and Avengers. All of these namespaces has the required label that is used by UDN. Now I'm going to create cluster UDN of layer 3 with primary role. As you can see, the cluster UDN is created and the network attachment definition has been created in DC and Marvel because we have selected only Marvel and DC for cluster UDN. Now I have created the separate UDN in Avengers namespace with topology layer 3. Now I'm deploying the pods in all of these namespaces. As you can see, all three pods are in the running status. I've exported the service as well, and all of them are node port services. Now I'm going to check the IP configuration inside these pods. As you can see, the UDN interface has been created, and now I'm going to check. As you can see, we are now connecting the Marvel service from a DC pod, which are in the same cluster UDN, and we could see that the output is 200 OK, which is expected. The pods should communicate with each other when they are inside the same cluster UDN. Now I am checking the vice versa traffic, and it is accessible as well, which is expected. Now I'm going to check the connectivity between the Avenger pod and the Marvel pod. And as you can see in the screen, we are not able to access Marvel service from the Avenger pod because Avengers has the separate UDN defined and Marvel is the part of the cluster UDN. So this shows that the isolation is working. I'm also trying to check the vice versa traffic from DC pod to Avengers service, and it is also not connecting, which is expected. So now I'm trying to check the default IP address connection. So 131.0.41 is the default IP address of the DC pod, which is provided by the UVN, OVN. And as you can see, it does not connect, which is expected because the primary interface, which is ETS0, should be for the Kubernetes health check. UDN network cannot communicate with default network of the pod. Now case 3. In case 3, we are going to check intra-pod communication and the reachability to the external world. So for that, I'm going to create the elephant namespace, and I have created UDN for the elephant namespace. As you can see, it is in the different subnet. Network attachment definition has been created. I'm now creating the elephant pod in the elephant namespace, and it is running fine. Now I'm exposing the deployment of the elephant to create the elephant service. Now I'm going to check the cluster IP connectivity from any one of the node in the cluster. So I'm going to replace the IP with the cluster IP, yes, and it should not work. As you can see, it times out. So that is expected. Cluster IP service should not be accessible from the nodes. Now I'm going to check the node port service IP. So from the node port, as you can see, the application is accessible, which is expected. Now I'm checking the node port IP and the node port of the elephant service from one of the node and the cluster. Previously I checked from the bashing host. So here also it works. So this is expected and all tests are passed successfully. The test cases that we have performed in the last slide. In case 1, blue pods can talk to its service using the UDN network, which is expected. And green pod cannot talk to the blue services, which is also expected in UDN network. In case 2, Marvel and DC pod can access each other, but they cannot talk to any other namespaces like Avengers. Similarly, Avengers pod cannot talk to Marvel and DC pods because Avengers has the separate UDN defined in this namespace. In case 3, cluster IP services is not accessible from the backend port, which is expected. And the node port type service is accessible externally. That is also expected. So I hope you all find this session insightful and helpful. And thank you all for watching this.